after drinking from this bottle, no one knows what was inside.
We have checked for fingerprints, but that's not enough. We need to know what had caused this.
Don't worry, we can collect victim blood and urine sample and use chromatography.
What?
Chromatography. It is a technique to separate different chemicals in the sample used to identify drugs, poison, or other substance in forensics analysis.
So today, we will show you how chromatography helps forensic scientists in analysis of blood and urine samples in forensic science.
Good day everyone! A single drop of blood or a small urine sample can reveal whether a person has taken drugs, consumed poison, or even misused medication. But how is this possible? The answer lies in chromatography. Chromatography is an analytical technique used to separate and identify substances in mixture. It is widely used in medicine, forensic science, and pharmaceutical analysis, because it helps detect substances present in complex biological samples. In this experiment, we use thin layer chromatography or TLC, which is a simple, rapid, and cost-effective type of chromatography commonly used for preliminary screening. TLC is particularly useful for analyzing blood and urine samples because these biological samples may contain drugs, metabolites, or toxic substances. Detecting this compound is essential for clinical diagnosis, drug monitoring, and forensic investigations. Therefore, this experiment aims to demonstrate the application of TLC in analyzing blood and urine samples and to highlight its importance as a reliable screening technique. Now, to better understand how thin layer chromatography works, let's move on to the theory behind this technique.
Thin layer chromatography or TLC is a simple and rapid analytical technique. It belongs to the family of planar chromatography because the separation occurs on a flat plate coated with a thin layer of adsorbent material. The TLC plate is usually coated with silica gels, although alumina can also be used. This layer acts as the stationary phase. A suitable solvent known as the mobile phase moves through the plate and carries the sample upward. The separation occurs because different compounds have different attractions or affinities for the stationary phase and the mobile phase. As a result, each compound moves at a different rate, allowing them to be separated into individual spots. The principle of TLC is based on the different interactions between each compound and the stationary phase and the mobile phase. First, a small amount of sample is spotted near the bottom of the TLC plate. The plate is then placed in a chamber containing the solvent. As the solvent arises by capillary action, it carries the compound upward. Compounds that interact strongly with the polar silica gel remain on the plate for a longer time and therefore move more slowly. These are usually more polar compounds. In contrast, compounds that are more soluble in the mobile phase and that interact less with the silica travel farther up the plate. This difference in migration causes the mixture to separate into distinct spots. After separation, each spot can be characterized using its retention factor or RF value. The RF value is calculated by dividing the distance traveled by the compound by the distance traveled by the solvent form, and RF value always range between 0 and 1. Under the same experimental conditions, compounds have characteristic RF values, which can be compared with non-reference standards for identifications. However, factors such as the solvent composition, stationary phase, and laboratory conditions can affect the RF value, so this condition must remain consistent for reliable result.
Now that we have understood the principle of chromatography, let's move on to methodology to see how it is actually used to analyze blood and urine samples. The process firstly begins with sample collection and storage. Blood or urine is collected in sterile containers and stored at the correct temperature to preserve the chemicals and prevent contamination, ensuring reliable laboratory results. Next is sample preparation. Since blood and urine contains proteins, salts, and many other substances, the target compound must first be extracted. This can be done by using protein precipitation, which removes protein, liquid-liquid extraction, which separates compounds based on their solubility, or solid phase extraction, which produce cleaner samples with higher selectivity and sensitivity. Once the sample is prepared, it is introduced into the chromatographic system. Thin layer chromatography (TLC) is commonly used for rapid, simple screening. Gas chromatography or GC is ideal for volatile compounds, while high-performance liquid chromatography (HPLC) is preferred for non-volatile or heat-sensitive substances. Finally, the separated compounds are detected using techniques such as UV visible detection, flame ionization detection (FID), or mass spectrometry (MS). The chromatogram is then compared with reference standards, allowing forensic scientists to accurately identify drugs, poisons, or other unknown substances in blood or urine samples.
Hello everyone, today we will discuss how we identify substance in biological sample using thin layer chromatography or TLC. Our core metric is the retention factor or RF value. It is calculated using a simple formula, which is RF equal to the distance solid travels over the distance solvent move. Because a substance can never travel further than the liquid solvent, this value is always between 0 and 1. By using a comparison method, running an unknown biological sample side by side with pure known chemical standards, we can directly match their RF values to identify the unknown compounds. Next, let's apply this method to a practical scenario. For example, analyzing a urine sample for cannabinoids. To establish our baseline, we rank two standards, which is the THC at an RF of 0.55, the purple spot, and its metabolite, the THC-COH at RF of 0.70, which is the blue spot. When we look at the patient's urine sample lane, we see a blue spot that perfectly aligns horizontally with our THC-COH standard at 0.70. Therefore, we can conclusively state that TLC successfully detects the THC metabolites in the patient's systems. Finally, we applied the same technique to a blood sample from a patient suspect of drug use, utilizing a 9:1 methanol to ammonia mobile phase. For this screening, we compare the sample against three distinct standards, which is caffeine, the RF is 0.25, paracetamol RF 0.48, and tramadol RF 0.62. Looking at the final lane, the spot from the blood sample perfectly matches the migration height of tramadol at RF of 0.62. This confirms the successful detections and identifications of tramadol in the patient.
To conclude, chromatography is one of the most important analytical techniques used in forensic science. It helps separate and identify different compounds found in complex samples such as blood and urine. Among the available methods, thin layer chromatography or TLC is simple, fast, and cost-effective, making it suitable for preliminary drug screening. By comparing the RF values of unknown samples with known standards, forensic scientists can identify drugs or toxic substances accurately. Overall, chromatography plays a vital role in providing reliable results that support forensic investigations and clinical analysis. Okay, so next we go to the applications. Chromatography has many important applications in forensic science. It is widely used to detect illegal drugs in blood and urine samples, helping investigators identify drug abuse or overdose cases. It is also used to identify poisons and toxic substances in forensic investigations, monitor medication levels in patients, and analyze unknown substances collected from crime scenes. In addition, chromatography supports biomedical research and postmortem toxicology by providing accurate and reliable chemical analysis. This application makes chromatography an essential tool in both forensic laboratories and healthcare settings.